Okay, Year 10, the purpose of this video is just to go through what I expect you to do with the questions for this week. So for the first section, I want you to write the chemical formula. So for example, iron 2 oxide, so remember the 2 here means that this is going to be an Fe2 plus. Okay, so if it's Fe2 plus, I'll write it up here, Fe2 plus, and it's oxide, so oxygen is in group 6, so that's going to be O2 minus. What would be the formula that these two ions would make? Well, iron is going to lose 2 electrons, oxygen is going to gain 2 electrons, so that's going to, you would need 1 of each. Okay, so it will be FeO. And then you need to state whether they are metals, simple covalent molecules, or ionic compounds. Now this is a metal and a non-metal, so this is ionic. Okay, and so you just need to go through those. Now calcium is just Ca, and that's just a metal, and ammonia is NH3, and you can look in here, well, in ammonia I've got nitrogen and hydrogen. Nitrogen and hydrogen are both non-metals, so we can work out which one it is. All right, so I think those first 15 are quite straightforward. And then section 2, you need to calculate the relative formula mass. So the relative formula mass is when you use the relative mass of each atom. So for H2O, you need to look on the periodic table for hydrogen. So the relative atomic mass of hydrogen is 1, and there are 2 of those, so it's going to be 1 plus 1 plus, and the relative atomic mass of oxygen is 16. So 1 plus 1 plus 16 equals 18. Okay, that's all you need to do. So you do that for all of those. Now for this one here, this is slightly tricky, but all you need to remember is that the 3 outside the brackets means that everything inside the brackets is multiplied by 3. So we can see that there are going to be 2 aluminium atoms, and then there will be, well, there's 1 sulfur inside the brackets, but there are 3 sets of brackets, so there'll be 3 sulfur atoms. And there are 4 oxygen atoms inside the brackets, and if there are 3 sets of those, there'll be 12 oxygen atoms. All right, that one's a little bit tricky. You know, if you didn't quite catch that, just pause it and watch it again. Empirical formula, you'll remember, is the simplest ratio. All right, so the ratio of carbon to hydrogen here is 10 to 20. The simplest ratio is 1 to 2, so you give the empirical formula as CH2. That's what I'm talking about. All right. Section 4, this is about chromatography. Now these questions are all fairly straightforward. You will need to remind yourself, I think, of some of the aspects of chromatography just to make sure you get these right, but I don't think that's going to take you very long. All right, but don't expect to be able to answer these questions just, you know, some of them, let's say for example, why is it a line in pencil? You might be able to remember that immediately. How do you calculate the RF value? You might not remember, so you need to look that up. Okay. Section 5. A pupil is a mixture of sand, copper sulfate, and water. How will she separate the sand out of the mixture? The sand is insoluble, so I think it should be straightforward to answer that one. Now, question 37. Once the sand has been removed, she tests the conductivity of the salt solution and finds it conducts electricity. Explain this observation. So at this point, I just want you to have it clear in your mind what is happening. All right, so what I'm going to do is I'm going to show you how this works. Okay, so what I've got set up here is a circuit. So this is my power supply here, and I've got 1 wire coming out of my power supply. The other wire goes into a bulb. All right, so we'll be able to see if the bulb lights up, electricity is conducted. Okay, so if I ignore these 2 for the moment, if I turn my power pack on and I connect these 2 together, it will complete the circuit. And the bulb comes on. So electricity is flowing, no problem. All right, now what I want to do is I want to test the conductivity of solid copper sulfate. Okay, so if I take my 2 ends of the circuit and I put those in there without them touching each other, so they're just going through the solid salt now, the bulb does not come on because the salt does not conduct electricity. And you know the salt doesn't conduct electricity because the ions in the salt are not able to move, because in a solid ionic compound, the ions are in a fixed position. Okay, now, what I've done is I've taken some of my copper sulfate, the salt, this blue salt, and I've dissolved it in water. And you can see that there in that lovely blue coloured solution. So what I'm going to do is I'm going to attach, in order to be able to test the conductivity of this, I'm going to use this piece of equipment here. I just attach one end of the circuit to this electrode, and I attach the other end of the circuit to this electrode. Okay, now, if I put this electrode, so these two electrodes into, let's put it into just water, and we see if it conducts electricity. So, does the bulb come on? No. So that water is not conducting electricity. Now, if I take the solution where I've dissolved some of the salt in there, so some of the copper sulfate in there, and I put that in, the bulb now comes on. All right? So you can see that because this one has got some of the salt, some of the copper sulfate dissolved into it, it conducts electricity. All right? Whereas this one does not. So if we go back to our question, once the sand has been removed, she tests the conductivity of the salt solution, finds it conducts electricity, explain this observation. I've just shown you that observation. That actually is true. I'm not just making it up. To explain it, you need to think about the ions. It's an ionic compound, copper sulfate. It now conducts electricity. Why? Because the ions are able to move in solution and conduct electricity. Okay? I think 38 is easy. This is about the temperature dependence of solubility. I don't think that's difficult. And you can have a good go at that one. And then this down here, this is all fairly straightforward, just remembering what specific words mean. Now, there is one issue that I would like to address. While marking your work from the last few weeks, it's become clear that there are a couple of misconceptions, a few of which are quite significant, and quite a number of you are making this misconception. And it is to do with electrical conductivity. Okay, and it's to do with the electrical conductivity of ionic compounds and the electrical conductivity of metals. So what I've got here is some pictures of what the structure of an ionic compound looks like and what it looks like in a metal. So my ionic compound is sodium chloride, and my metal is just sodium. Okay, now, as a solid, this will not conduct electricity. Why not? Because the ions are not free to move. They vibrate around a fixed position, so the ions do not move. Now, notice there how I said the ions do not move. At no point did I say the word electron. Okay, an electron has been transferred from here to here, but there's no electrons anywhere here. Okay, it's all to do with the movement of the ions. However, in a metal, this will conduct electricity, and that's because we have this sea of delocalized electrons. Okay, this is the sea of delocalized electrons. Okay, and these can move and conduct electricity. All right, so if I now melt this, okay, if I turn this into a liquid, NaCl liquid, it can conduct electricity. Okay, as a solid it can't, but as a liquid it can because, and listen very carefully, because now the ions are free to move. You see how I didn't mention electrons again? And that's because when we're thinking about conductivity, for ionic compounds, the conductivity depends on the movement of ions. Whereas in a metal, the conductivity depends on the movement of electrons. So I see a lot of answers which say, does an ionic solid conduct electricity? And the answer will be no, because there are no electrons which are free to move. Okay, and that's a wrong answer, because the conductivity of ionic compounds is nothing to do with electrons. It's all to do with the movement of the ions. Okay, and you know that makes sense because sodium chloride as a liquid will conduct electricity, but it's not because of electrons. It's because the ions are free to move. Okay, so whenever you're talking about ionic compounds, I don't want to see you talk. Whenever you're talking about the electrical conductivity of ionic compounds, I don't want to see you talking about the movement of electrons. Okay, unless you're talking about, you know, in the wires of the circuit. But in terms of the actual thing we're talking about, it's the movement of the ions. Metals, it's all about electrons. And the other misconception I want to talk about is to do with melting and boiling points. Okay, so we've got three main types of compound. We've got ionic, we've got covalent, and we've got metals. Okay, now obviously covalent includes simple molecules, giant covalent lattices, and polymers. All right, but the problem is that if I ask the question, let's say, is the melting point of an ionic compound generally high or low? It is generally very high. What's the reason? Now, you know that the reason is the strong electrostatic attraction between the ions requires a lot of energy to overcome. But people are now starting to talk about intermolecular forces, strong intermolecular forces. And that is wrong, because the clue is molecular, which means molecules, which means simple covalent molecule. All right, and simple covalent molecules are things like H2O, CO2, NH3. All right, and these have got weak intermolecular forces. But in terms of ionic compounds, you cannot talk about intermolecular forces because there are no ionic molecules. An ionic compound is this big, giant ionic lattice, so don't make that mistake. All right, apart from that, you're all doing great work, so keep it up.